Okay, let me begin. Are there questions? Okay, so if not, let me start. So let me first review where we were last time. So we had this global ADS geometry. So this is a t equal to 0 slice of ADS with a boundary. And then on the boundary, we had separated out a region, okay, which we call P prime, and the complement was Q prime. So let me draw those. This was P prime, complement was, sorry, yeah, Q prime. And then we had qubits on the boundary, which are the ends of the links. And then you had also qubits in the bulk, which is denoted by crosses. Okay. And then we said that let's just take an arbitrary cut through this. Okay, cut means that it shouldn't pass through the vortices. Okay, but it avoids the vortices. So let me draw some arbitrary cut. Like this, okay, which we call C. And then this bulk region I'll call P, and this bulk region I'll call Q. And then you also assign index labels. So these qubits, okay, generate a Hilbert space, and the basis of Hilbert space we denote it by the index A over here. Similarly, these bulk qubits generate a basis of Hilbert space, which we denoted by B. Now C cuts a set of links, okay, because it avoids the vortices. So let me draw those links. So these links, okay, each of them have a qubit, of course, right? So they have also a Hilbert space, and that Hilbert space basis I labeled by I. And then these qubits have a Hilbert space, which is denoted by A. Small in the basis I labeled by small a, and these qubits have a Hilbert space whose basis I labeled by B. Then we gave some definitions. So M IAA, this is given by the product of perfect tensors in P. And its free indices are I, okay, because these are a set of indices, that's the boundary of P. Then the bulk indices, which are of course free, okay, the A, and then the boundary indices, because the links, these are the ends of the links, right? So whatever index that carries, that's A. And similarly, we introduced N I, B, P. This is a product of perfect tensors inserts in Q. And let's suppose that C cuts NC links. Okay, where some NC is some number, and that depends on, of course, on how you choose the cut. So then we took a bulk state, which is a product state. Okay, later today I'll discuss what happens if it's not a product. Okay. So let's take a bulk state, which is of the form PA times A times QB times B. Okay. And throughout today's lecture, I'll use summation convention. So repeated indices are summed over. And then we showed that if we use the bulk to boundary map, which for this code is given by just a product of all perfect tensors in the bulk, okay, whose free indices will be the bulk indices, okay, which are A and B, and the boundary indices, small a and small b. Then this bulk state maps to the following boundary state. This maps to the boundary state Pi times Qi, okay, and we'll define what these Pi and Qi are. Okay. So what was Pi? Pi was MIA A PA times A. Okay, so it has this index I. And similarly, Qi was defined by NIBB BB times B. And then so this is the state in the bulk. Okay. So from this, we can calculate the density matrix for this state. So density matrix, okay, everything is in the boundary now, okay, because this is really a state in the boundary. Even though it's labeled by P, Q, and I, right, the actual state is in the boundary because you can see that it's a map. This is a state in the boundary, and this is also a state in the boundary. Okay. So rho of P, okay, so we define the rho of P prime, okay, which means that we trace out the degrees of freedom in B, okay, and that was given by Pi, Pj, and Qj, Qi. So these Pi's and Pj's are now supported only on the on this part A, because we are tracing out the degrees of freedom here. Okay. And we calculated S of rho. And what we found is that S of rho is less than S of rho of P prime. This is less than or equal to NC log 2. And this equality is saturated if MIA A and NIB B are isometries from, so M has to be isometric from the space of IA to A, and N has to be isometric from the space IB to B. Okay, so this is where we stop last time. Are there questions on this?
Sir, one question.
Yes.
Like in the last class, we saw that the perfect tensors are isometric. Means we can write the perfect tensors as isometric. So if M and N are product of perfect tensors, shouldn't they be automatically isometric? Why is it a like different condition or separate condition?
Because it could, I mean, it's not always the perfect tensors are isometries. You have to make sure that the number of output legs is more than the number of input legs, right?
Okay.
And it's not guaranteed that M and N can always be regarded that way, right? That
But means the perfect tensor product, they may not have that property.
Exactly, right?
Okay.
Each of them may not have the number of output legs more than a number of input legs.
Okay.
And I think it will become clear today when I discuss how to construct these minimal cut. And we'll see that the perfect tensor doesn't necessarily mean that anything you can do at this in isometry, because this is a condition that you have to maintain. Okay, so now the point is, if it's clear that if M, write the index, if these are isometries, then C must be the minimal cut. Why? Because if M and N are isometries, okay, then you have seen last time that this equality is saturated. But this is of course an inequality. So for any C, okay, irrespective of whether M and N are isometries or not, S of rho has to be less than or equal to NC log 2. Right? So once you have found a C for which M and N are isometries, okay, there cannot be another C for which NC is lower. Okay, because that will be contradictory. Because on the one hand you have equality, on the other hand you are saying you have an inequality, you have an upper bound which is lower than what we had earlier. So that's not possible. So this means that if we have found a cut for which these are isometries, then it's guaranteed that this is a minimal cut. But a converse is not automatic. Namely, a minimal cut does not imply that MIAA and NIBB are isometries. Because there may be no cut for which this bound is saturated. So the question is, can you prove this? If we can, then this will lead to RT formula. Right? Because the RT formula is essentially the equality of the two sides. So later we'll address this question. But before that, we'll study some other consequences of Mn being isometry. And then we'll come back. So this before discussing the proof or lack of proof. Okay, we'll see what the best way one can do. The first point I'd like to note here, okay, it should be obvious from whatever we have discussed, that the formula or whatever analysis we did does not require P prime and Q prime to be simply connected, to be connected. Okay. So let me give an example. Okay. So imagine that our P prime is a set of two disconnected regions. We call this P1 prime and P2 prime. And similarly, Q prime is a combination of two disconnected regions. So P prime is P1 prime union P2 prime, and Q prime is Q1 prime union Q2 prime. Now consider any cut in this geometry whose boundaries coincide with the boundary of P prime. Now, boundary of P prime here is a union of 4 points, boundary of P1 prime and boundary of P2 prime. Okay, so these 4 points. So the cut can be like this. Okay, cut also doesn't have to be connected, so you can have a cut like this. Let me call it C1 and C2. Okay. And then we can have C equal to C1 union C2. Or we can have a cut like this. C1 prime and C2 prime, and C prime will be C1 prime union C2 prime. Okay. And the general analysis we did, okay, will be valid both for C and C prime. Okay, the inequality will be valid both for C and C prime. Okay. You don't really have to change anything. Okay, basically what will happen now is that the role of P for this pair of cuts, the role of P will be played by the union of this and this, and the role of Q will be played by the complement, which is this whole region. On the other hand, if we choose this pair of cuts, then the role of P will be played by this region, and the role of Q will be played by this region together with this region. But you can easily convince yourself that nothing that you have done in your analysis will change. Okay. For example, for this pair of cuts, the label A, capital A, will refer to both the Hilbert space here and the Hilbert space there. Okay, so it will be the product of these two Hilbert spaces. That's the basis that capital A will label. Okay. And capital B will label the whole region. Whereas if we take this pair of cuts, then the capital A will represent this whole region, and capital B will represent these two regions. But nothing has to be changed in the analysis.
Then in this case, when we construct the boundary states Pi, they will be like Pi means Pi1 product Pi2, or like how?
Yeah, exactly. That's right. So boundary state, right, will be a, you don't have enough to write it as a product. It will be supported on these qubits as well as these qubits. Right. So the A will now stand for these and these. Okay. These collection of qubits will be labeled by small a.
But P and Q will still be entangled, right?
Yes. Yes. So you don't have to. P will have exactly the same definition, right?
Okay.
Except that the A in A will be running over this and this.
Right. That's
okay. But that formula is not going to change at all. Okay. So then S of rho, this equation S of rho is less than or equal to NC log 2 will hold for both kinds of cuts. And the minimal cut will require searching among both kinds of cuts. And it's only for the minimal cut that there is a possibility that M and N are isometries, but it's not guaranteed.
So the length of, let's say, the C1 cut will depend on both P1 prime and P2 prime, right?
Yes, indeed.
Yeah.
Yeah. So specifying P prime means you specify both P1 prime and P2 prime. So in this case, for example, the length of the cut will be C1 plus C2, the length of this plus length of this.
Yeah, I was asking individually, length of only C1 will depend both on P1 prime and P2 prime, because since they can be entangled, the states on P1 prime could be entangled with those on P2 prime. We cannot just look at P1 prime and specify the length of C1.
No. Yeah. So the point is that, let me put it this way, that the C1, of course, can be chosen anything to be anything, right? If it's not a minimal cut, it's you who choose C1. I can choose C1 arbitrarily, C2 arbitrarily. But for the minimal cut, indeed, it's not that you minimize C1 separately. The minimal cut will depend, the C1 and C2 shape will depend on both P1 prime and P2 prime. Yeah. So you don't separately minimize. Yeah. Okay, so now we'll try to address another question. Namely, what happens if the bulk state is not a product state? So let's take the bulk state to be FAB A times B. And let's see what it maps to. So bulk to boundary isometry is given by this following tensor MIAA NIBB. Okay. You have to think of this as a map from AB pair to AB pair. This is the bulk to boundary map. I have already summed over I. Okay, in fact, this was our starting point in doing the whole analysis that we did last time. Okay, so this was the bulk to boundary map, and then we rewrote as a sum over I into Pi times Qi. So then it's easy to find out what the image of this will be in the bulk. So in the boundary, so image, let me call this psi. Image of psi in the boundary will be given by I think I again made the mistake. This is IA and then IB. And unfortunately, I have written it in the wrong way. I mean, it's a map is from IA to A, right? So as a matrix, you should think of this as the A as the first index and I times I and capital A as the second index, right? Because it maps from this product to the boundary, which is small a, right? Another way of saying this is that typically the number of states that are contained here is much less than the number of states that is labeled by this small a. Anyway, so let's proceed with this convention. Okay. So the state will be MIAA. I need some more space, so let me try to lift it. MIAA NIBB, then FAB A times B. Okay, because FAB was the input, and these I is summed over, right? Because this that's coming from here. So this converts the index capital A capital B to small a small b. Okay, so this is the linear combination of basis states, and that's the state in the bound. So now let's try to construct row of P prime. So let me write this. So it will be MIAA. Okay, we first write the state and then its complex conjugate. Then M star I prime A prime N star I prime B prime F star A prime B prime. So far it's fine. Then you have A prime, and if we are just trying to calculate the density matrix, then I'll have B prime. We will have, let me write this and then I'll reverse it. We would have had B prime, but because you are trying to trace out the degrees of freedom in the complement of P prime, which is Q prime, we have to bring B prime on this side. So let me do that. So this B prime will come on this side. And once it comes on this side, it produces delta B prime. Is this clear? But now you immediately see that assuming that Riemann and isometries, we are assuming here the Riemann and isometries. So let me write this. Assume then this and this, these factors together, because you have a sum over B, right? Delta B prime sets B prime equal to B. You have sum over B, and then because if it's an isometry, this is n dagger n is identity. So this product basically becomes delta I prime, delta B prime. Is this clear?
So isn't the ordering important? You said that n dagger n is identity.
Yeah.
It's not.
Yes, it's important. So when you think of n as a matrix, okay, as I said, I prime and B prime are the second index. B prime is small b prime is the first index.
Right.
Okay, and now if you calculate n dagger n, you will see that it's the B and B prime index that is contracted. Okay. The general rule of thumb, okay, is that when you have this m dagger m equal to 1 or n dagger n equal to 1, the index that is contracted, right, runs over the larger Hilbert space.
Okay.
So that's the general rule, okay, because it runs in the target Hilbert space. So here, the larger Hilbert space in this set is a B, right? These are belonging to the boundary. I and B, okay, this is a smaller set.
Yeah, right.
So once the B and B prime are contracted, right, then that's what the isometry relation tells us.
Okay.
And that's sort
So
of
that determines the ordering, means that itself intrinsically determines how it is ordered.
Exactly. So the point is, so this, for example, right, you should think about a matrix whose first index is B, second index is IB.
Right.
Okay. So because the first index is B, right, and here when you think of the n dagger, okay, the second index is B. So the second index of n dagger gets contracted to the first index of n, right? That's n dagger n.
Right. Okay.
I think for M we'll do it explicitly in the next slide. So this is then given by M I A M star I A prime because I prime became equal to I, and then F A B, F star B prime became B, so F star A prime B, and then A prime. Yeah, I think I more or less have got everything correct, right? The indices are all contracted. I contracted, A contracted, A prime contracted. Yeah. Okay, so this is, so I'll just take this and write in the next page again. So rho of P prime is M I A M star I A prime. Okay, I should have done one more thing here. You see this product over here. This is the density matrix of this state after tracing over B, right? Because B is summed over. So this is the basis in the bulk on the logical qubits. So if you trace out B, you will get a density matrix which is precisely F A B, F star A prime B, okay, and then A prime. So this one I can interpret as rho bulk A prime. Is this point clear? Okay, that's just the density matrix of this after when you trace out B. So I'll write it that way. Rho bulk A prime and then A prime. So this quantity I'll define as rho A prime. And just think of this as a matrix. Okay, matrix where with A and A prime index running over the Hilbert space of the boundary of the P prime segment of the boundary. Now we'll also represent these as a matrix. So we define M A I A. Okay, so here I have really written it correctly as a matrix. Okay. So here, this is the second index, this is the first index. Okay. And that's because this is the input and this is out, right? So when you think of this as a matrix, you should really write it this way. So then we can write rho in the matrix form. Okay, this rho A prime. This is a matrix form of matrix interpretation of rho. So this I can write as M, because A is the first index, IA is the second index. Then rho bulk times identity. Okay, so what is identity? This is in the IJ space. Delta IJ. Okay, why delta IJ? Because the I index is contracted. And then M dagger. Okay, maybe I should write it in a little neater way. Okay, so this one, okay, let's say where it follows from, where I'm basically writing rho A prime as M A IA, then rho bulk A prime delta IJ, and this one I'm writing as M star J A prime, M star A prime J A prime, but this is the same as M dagger J A prime and A. And now you see that you have a matrix product because the first index is A. Okay, that's the here. Okay. Then the IA index is contracted with I and A. Okay. Then you have A prime J, okay, and A prime J. Sorry, what did I? Yeah. So J A prime is contracted with J A prime. Yeah. Okay, and then you have this. This should be A. Okay. And that's where this equation follows. This is a matrix form of this equation. Okay. This is written in components. This is a matrix form. So given this, we are now going to calculate the entanglement entropy. Okay, I should have said that all of these is really up to proportionality constant. Okay, so let me write it once and for all. So these are all really proportionality constant. Because you remember that you have this 1 over root d, right? Or in this case, 1 over root 2 factors that come in when you transfer the input leg to output leg. Okay. And so those factors will accumulate. Okay, but we are not bothering about those because ultimately rho will be normalized anyway by putting trace rho equal to 1. Okay, so these are all up to that overall normalization. So whenever you take, say, M and N are isometries, right? That's also up to this overall normalization because you have to normalize them appropriately. Okay, so now let's calculate S of rho. Is trace minus trace of rho log rho. And rho is given by this. M dagger M is identity. And inside the trace, you can cyclically permute. So M dagger you can bring on this side. Okay. So for example, if you have a trace of rho to the M, right, what do you have? So this is M times this time M dagger, then again M times this times M dagger. Okay. In the middle, all the M dagger M will become identity. Okay. And the last M dagger we can bring on the front and set M dagger M equal to identity. Okay. So for any function of rho, okay, we can do this. Okay. And so this then will be given, okay, by doing this as minus trace. Okay. So far, I haven't used the fact that M is an isometry, right? I use the fact that N is an isometry, but I haven't used that M is an isometry. Now I'm using it, okay, because I'll set M dagger M equal to 1. So this is minus trace. Let me write rho prime log rho prime. What is rho prime? Okay. So rho prime by definition is rho bulk times identity. Okay, and now it's straightforward to evaluate this. Okay, if you have a product, a density matrix that is a product, a direct product of two density matrices. okay, in two Hilbert spaces, then it is the sum of the corresponding entanglement entropies. So this is given by minus trace of rho bulk log rho bulk, and then for the identity, okay, that answer is minus 2, sorry, minus NC log 2. Okay. So this then I can write as S bulk, because this is the density matrix of the bulk. This is the entropy of the bulk density matrix, okay, plus, sorry, this should have been plus NC log 2. So this is the RT formula, okay, and this is an extra piece that got added. Okay. We didn't see it from earlier in the RT formula, but I'll define describe a refined version of RT formula where we'll actually see this appear. Okay, and this refined version, in fact, was derived independently of this holographic code. In fact, this refined version was derived earlier than this quantum error correction approach. Okay, but we'll discuss this maybe later today. Okay, other questions? So the net upshot of this analysis is that if the bulk state is entangled, then in the best of cases, okay, which is when M and N are isometries, you get the classical Liu-Takayanagi formula, the A over 4Gn, which is represented by this NC log 2. Okay, but you have an added contribution, which is the bulk entanglement. Okay, so if the bulk state itself was entangled, then the entanglement entropy of that state gets added. Is this okay? Are there questions?
In the previous slide,
Yes.
this log rho bulk, then it will be log rho bulk plus log identity, right? Within the log.
Yeah, but because it's in the product Hilbert space, right?
Yeah.
Okay. It will be the sum of the two.
Okay.
Okay. See, it's not a product of matrices, right? If it's a easy exercise to check, right? If you have a product Hilbert space, right, and if the density matrix is given by the product of two density matrices, right, one in the first Hilbert space, the other one in the second Hilbert space,
Yeah.
then the entanglement entropy, I mean, this computation just gets it's as if you are computing the entanglement entropy of this plus the entanglement entropy of this.
Okay.
So the entanglement entropy of this is given here. This traces over the bulk Hilbert space, okay, over the space level by A, and this is coming from the trace over the this cut Hilbert space, right? And that's why you get this number NC. Okay, it's basically log of 2.
Yeah, the reason why I asked is that earlier you didn't this formula NC log 2, this part.
Yes.
This we derived from this log of trace of log rho was trace of rank rho, means the S rho has to be less than, from that formula we derived, right? From the rank of rho we derived, right? Means,
yeah, but that was the inequality, right? If it was an equality, then basically rho was proportional to identity matrix.
Oh, okay. Oh,
okay. That is this identity matrix, as you see here. Again, I should have written it as a proportionality, right? Because identity proportional to identity means it's actually this 1 over the rank, right? Each entry is 1 over rank, because trace, of course, has to be 1.
Okay.
So it's a direct product, right? Earlier we didn't see this. We only saw this, right? This was basically rank 1. I mean, we didn't see this meaning because it's a product space, right? Row
Yeah.
bulk basically had rank 1.
Okay.
Okay, so these didn't contribute, and this contributed this NC log.
So this part is actually basically gives the log of 1 over R, which will transfer to this result in C log.
Yes, exactly.
Log of 1 over R.
Yeah, 1 over 2 to the NC, right? Each entry is log of 1 over 2 to the NC.
Okay, okay. Yeah, okay.
And then when you calculate this trace, right, you get 2 to the NC, and then each entry is 1 over 2 to the NC. So you get 1 over 2 to the NC log of 1 over 2 to the NC. Right? That's where this is coming from.
Excuse me, sir. Will not the proportionality constant of that equation rho prime proportional to rho bulk tensor I will contribute some factor in the last line?
Yeah, see, the point is that, yeah, here I have written as a proportionality constant, but as long as trace of rho bulk is 1, right? If rho bulk is normalized or trace of rho bulk is 1, the proportionality constant is just 1 over 2 to the NC. Right?
Okay.
So the trace, I mean, the proportionality constant is fixed by requiring the trace of rho prime is 1. Now, trace of rho prime is the product of trace of rho bulk and trace of identity. Rho bulk, you can just normalize that trace of rho bulk is 1. Okay, that is easy if this state was normalized, right? That is automatic. If psi was a normalized state, then rho bulk that I have defined, right? This one automatically has 0 unit trace, right? Because you just sum over, you set A equal to A prime and sum over A and B. That's the norm of this state. That's 1. So the non-trivial part is that this I, instead of I, here you have 1 over 2 to the NC, each entry. And that's what leads to this. Is this clear?
Yes, sir. Clear.
Any other question? Okay. So now we come to the question that we should have addressed earlier, but let me do it now. And that is it possible to find a cut for which M IAA N IBB are isometries? So to address this, we will now, I'll tell you what results are known for this. Okay. But for this, you have to get some idea of how one goes about when addressing this question. So this is done by using something called greedy algorithm. And this basically attempts to find the minimal cut for which M or N is an isometry. So notice that it's or, okay, and I'll explain why this is. Okay. So let's start with M. Okay, that is, so you have to basically do the analysis separately for P prime and Q prime. Okay, I'll explain what this means. Okay, M will refer to P prime and N will refer to Q prime. So let me draw this figure again. And the qubits. And now we have to also identify some region called P prime. Okay. So let's say that this region is P prime. Okay, that this is P prime, okay, in between these. And from each of these boundary qubits, right? We have a link coming out, right? That's the way we define these boundary points, right? Because where the links cut the artificial boundary that we have put. So let me draw those links. So the idea here is that we will start with a cut, okay, which is obvious and isometric, okay, for which the map is obvious and isometric, okay, but it will not be minimal, and it will be only for one side, okay, either M or N. In this case, we are focusing on M. Okay. So we'll start with a cut which is obvious and isometric, okay, and then we try to deform it, okay, so that we reduce the number of cut lengths, preserving the condition that it's an isometric. And we keep doing it till we cannot do it anymore. Okay, so that's the general algorithm, but let me say how exactly it's done. So the starting cut is the one where you only cut the links that come out of the boundary points. So this is a starting cut. So start with trivial cut. So here you only have the index I, no capital A, right? Because there are no bulk points involved. Okay, between this and P, the P prime. So this is our P prime, right? So between this cut and P prime, there are no bulk points. Okay. So IA. So for this, let me write MIA is just delta IA, right? Each link is just directly connected to the boundary qubit. So this is delta IA. So this is obvious and isometric. Here is identity map. Is that clear? So this will be our starting cut. Then the second step is that move the cut one step at a time. Cut through bulk points. Let me say through one bulk point at a time. Such that at least 3 links are directed from the bulk point towards P prime. Okay, so let me describe the first step, okay, by an example. So let's suppose So from a bulk point, you remember that there are 5 links coming out. Okay, because one input comes from the bulk point itself, and then there are five links. Suppose you have a situation like this. Suppose the original cut was going like this. Okay, so P prime is on this side, and this side is the bulk. Then we can move the cut across this, because there are 3 links that are directed towards P prime. From this bulk point, there are 3 links that are directed towards P prime. Okay, so this, then the move that is involved is that starting from this, we move to, we keep everything else unchanged, but just move the cut to this point. So this has 2 properties. So property A is that it reduces the number of links cut. Right, because at least 3, so that means if 3 links were directed towards P prime, right, then the original cut was cutting at least 3 links. Okay, when you move across, okay, there are 5 links coming out altogether, so the cut will now cut at most 2 links. So you certainly reduce the number of cuts, number of cut links. The second property, okay, which is important, is that the vertex is an isometry from the bulk towards P. Okay, why? Because the number of outputs, right, this is P prime. Number of outputs is at least 3 from here, right? Because the at least 3 are directed towards P prime. Okay. So this is an isometry. Okay. So this means that the new cut, this implies that the new cut has MIAA and isometry. Is that clear? So we have solved, we have improved things a little bit, because we have reduced the number of cuts and we have not destroyed the property that M is an isometry, right? M still remains an isometry. So the idea is that we repeat this. We repeat this process. And we stop when we cannot move the cut anymore. And what one can show that, you see, initially there are many choices, right? I mean, you could have moved, I mean, there are many cuts, many neighboring bulk vertices, which will have 3 lines, at least 3 lines directed towards P prime, right? So you could move the cut through any of those points. So the order in which you do things is ambiguous. But what one can show is that the end product, okay, where you end at the by doing this, that is unique. Okay, so there is an ambiguity there. So you call this C dot. Call this cut and what we have maintained throughout this is that MIAA for that cut C naught is an isometry. Because composition of isometry is an isometry, and at every step, you are basically composing an isometry with the previous isometry. Okay, so M remains an isometry. Now,
Sir,
yes.
sorry, sir. So when you're saying that we stop when we cannot move the cut anymore, by that, do you mean that the property 1 is violated? Like it will increase actually the number of.
Exactly, yeah. That you will not have any more vortex, right, of this kind. We'll have 2 or 1 line coming out, and the 3 or 4 lines on the other side.
Okay.
Okay, if it happens for all of the vortices, then you cannot move the curtain, right?
Right. Okay.
So now we start from Q prime and carry out the same procedure. And suppose we have to stop at C naught prime, and it is again guaranteed that NIBB for C naught prime is an isometry. Okay. So now comes the main point. So if C naught coincides with C naught prime, C naught prime, then we are done. Because then we have got a curve, we have got a cut for which both M and N are isometries. And then it's guaranteed that that is the minimal cut, and all the properties that we want hold. But suppose they don't. If C naught and C naught prime doesn't coincide, we still have some useful results. Okay, so which I'll state but not prove. So let's define C naught intersection C naught prime as the collection of links that are common to both C naught and C naught prime. Then one can show S of rho P prime has a lower bound and that is n C0 intersection C0 prime log 2. Earlier you had upper bounds. Okay, so let me remind you what the upper bounds were. So S of rho p prime, of course, is bound from above by n C0 log 2 and also n C0 prime log 2. This is true for any cut, in particular for C0 and C0 prime. Okay. But this is a lower bound. Okay, that if you have if you have a certain number of common cuts, common lengths, okay, which are cut both by C0 and C0 prime, okay, then that number times log 2 provides a lower bound. And so the idea is that if this one C0 intersection C0 prime is close to n C0 or n C0 prime, then we have a narrow range. Narrow range of allowed values of S rho. So you can improve the bound. Okay. Nevertheless, for this code, the exact equality does not hold in all cases. Okay. So this question will return at the end of today's lecture.
So,
yes.
Which equality do you mean here? The RT formula equality?
Yeah, exactly. The equality of n C0 to intersection C0 prime and n C0, right? Which means basically that C0 and C0 prime are equal. Okay,
Okay. You just mean it's an approximation.
Yeah. This equality does not hold. I mean, if you look at a paper, there are arguments which show under what condition that if you have a very large number of, if you take the large volume limit, then the error is small compared to the volume. So there are various limits in which you can improve this equality, right? The C0 and the difference becomes small compared to the actual values. Okay. But still, it doesn't hold in all cases. Okay. So this code is a good model, good toy model, but it doesn't satisfy all the properties that are desired.
Also, this algorithm only works well for a connected surface, right?
No, it works for even disconnected, right? Because if the disconnected ones, right, what you have to do is, suppose we go back. Suppose it's disconnected, right? You have two pieces. Then you begin from this cut union that cut, right? And start deforming.
Yeah, but the C0 prime can never be overlapping with C0 then.
It could. Suppose a join, right? It could happen that when you deform this, there's two cuts join at some point.
Well, I'm not sure, but maybe okay.
Yeah, meaning it's a complicated process, right? I mean, but this one can study what happens. as you keep deforming. Okay, I think if you look at the original paper, I mean, they discuss things in detail. I mean, they are, because they do discuss also the disjoint union of regions. But as I said, eventually it doesn't quite work, okay, because this equality doesn't hold in all cases.
Okay, but even in the case where the equality is not exactly true, this C0 intersection C0 prime will be my minimal cut, right? Because that condition still holds that if M and N are isometries, then it will be like some minimal cut. We have the minimal cut.
No, but this is intersection. This is not a cut. The C0 intersection C0 prime, right, is not really a cut, right? It's the number of common links, but none of these are cuts. C0 is a cut, C0 prime is a cut. But the intersection is not a cut. It may have just one link in common, for example, right?
Okay.
Okay, then one link is not a cut, right?
Yeah.
Yeah, so it's not C0 intersection C0 prime is not a minimal cut because it's just not a cut.
So the statement that we made earlier that if M and N are isometries, then we have a minimal cut, that is also like subject to some condition.
No, but there is no cut for which M and N are common, right? See, if C0 and C0 prime coincide, right, then it's for that cut. See, the way I have described it, M starts from one side, N starts from the other side, right?
Oh.
If C0 and C0 prime does not coincide, right, then M refers to C0 or N refers to C0 prime.
Okay.
Right? Whereas what we did earlier, right, we assumed there is one cut for which M describes one side of the isometry and N describes the other side of the isometry.
So we started from the cut in that case.
Exactly, right.
Okay.
But if the cut, if they refer to different cuts, right, then that proof doesn't work.
Okay.
So only if C0 and C0 prime coincide, then the proof works.
Right. Yeah. That's why I was asking.
Yeah. So if the C0 and C0 prime doesn't coincide, then the proof doesn't work. Right? C0 is still an isometry with for the as far as the map to P prime goes.
Okay.
And for C0 prime, it's still an isometry as far as the map to Q prime goes. But there is no cut for which both sides are isometries.
Okay.
Okay, any other question?
So this might be true that although the algorithm does not produce a cut that coincides, I mean, C0 and the algorithm did not produce C0 and C0 prime that coincide, but there actually exists a cut which which provides an isometry between P prime and A and Q prime and B.
Yeah, it could happen. I'm not completely sure what the full set of results are, but I think in this paper they discuss it in detail, right? What is possible and what is not possible. But at least from whatever I have said so far, right, it's certainly possible that there is a cut for which both are isometries, and we just don't find it using this greedy algorithm.
Yeah.
Okay, now for a little while we will go back to geometry because we want to now understand what exactly is expected. Okay, now that we have learned some more details. And so we want to now discuss I should say quantum version, okay, a more precise version of Reuter-Koenig formula. But precise will be inside quotes because we will see that it's still not so precise. So, but we will not do it work in general. So you will work on the t=0 slice of static geometry. Now, a more general version of this is known, where you can have geometries which are not static and you don't necessarily work in that t=0 slice. Okay, but when any on any space like any Cauchy hypersurface, that means any space like slice. So the general formula, otherwise we'll need what is called HRT formula. This is Hobini, Rangamani, and Takanagi. Okay, they generalize the RT formula for away from static geometry and the t=0 slice. Okay, but we will not consider it. We will consider only t=0 slice and static geometry. So let's consider some region of the bulk of the boundary, some region R on the boundary, not necessarily connected. We'll be working throughout on t=0 slice. So now we consider a surface. Well, surface means generalized surface, right? In ADS3, it's just a line. W in the bulk, that is so this homologous is slightly more restrictive than what we had said earlier, that the boundary of R should coincide with the boundary of this surface W. So homologous basically means that W should be continuously deformable to R. So this is stronger in global ADS is the same, but otherwise in general it is stronger than just demanding that the boundaries coincide. Okay, so this is the symbol for boundary. Okay. So let me give an example. So let's suppose that we have this boundary geometry. Let's call this R. And let's imagine that there is a black hole sitting in the interior. Okay, so it's not just global ADS, but there is a black hole in the interior of ADS. Now, let's see what are the allowed Ws. So this one, so this is allowed. Okay, why? Because it can be continuously deformed to R. And of course, the boundary of W coincides with the boundary of R. But this one, this is not allowed. Because the boundary of this, of course, coincides with the boundary of R. Okay, but this cannot be continuously deformed to this. So that's why this surface is not allowed because it's not homologous. But if you take the union of this and the black hole horizon, okay, then that's again allowed because you can use the black hole horizon to cancel a part of this. Okay, you can deform it, okay, by wrapping the black hole horizon and then deforming it to R. Okay. So union of this and black hole horizon will be an allowed choice. So when you extremize, okay, you have to extremize over all these surfaces. So this is example 1. Example 2 we had already seen earlier. Let me draw this again. So you could have R which is disconnected. So you can have R1, R2. So one choice of W will be this. Okay, union of these two. Or you can have the union of these two. So W1, W2, and you can call this W1 prime, W2 prime. Okay, so W1 prime union W2 prime, and the other one W1 union W2 are both allowed. Choice. Okay, I should have said here R is R1, R here is the union of R1 and R2. That's the definition. Okay, so this is the, I have so far said what are the allowed choice of this W. Okay, what we do with it, I'm going to say in the next.
So what did you say regarding the first example with the horizon?
That this one is not allowed because it cannot be continuously deformed to R, right? But what we can do is that we can deform to R, provided we leave out this black hole horizon, right? So you can deform it like this. Let me use this. So this surface can be deformed to a surface like this. Right? And then you can.
Yeah, we'll include that then.
Yeah. So then the point is, so this part can be deformed to R, right? But this is left over. So that if you take the union of this and the black hole horizon in the opposite direction, then that can cancel this part, and that is deformable to R. So while this red surface is not deformable to R, okay, the union of this and the black hole horizon can still be deformed to R.
Here we are treating the black hole as a classical singularity, right?
Yeah. Basically, you wrap the horizon, right? You think of the region inside the horizon as inaccessible.
Yeah.
Okay. So you as if there is a hole in between, right? So you have to wrap around that hole. Okay, you have to cancel the wrapping around the hole in order to be able to deform this red curve to R.
Yeah. Okay.
Okay. So now, given this W, so take any choice of W. Okay. So now we'll consider SW. as defined. So this is a definition. Area of W over 4Gn plus, oh, I should have defined this. Let me do it. So let me define V is the region enclosed by W and R. Okay. So if W is homologous to R, right? If it can be continuously deformed to R, then that means there is some region of the bulk that is sitting in between W and R. Okay, for example, here, if this is the choice of W, right, then the region is this one. Okay. Here, if the choice of W is W1 prime times W2 prime, then the region in the bulk is this one, union this one. On the other hand, if it's this one, right, W1 union W2, then the region which is between union of W1 and W2 and between R1 and R2 is this whole region. Okay. So that's our V. Okay, so V is a region enclosed by W and R. Is that clear? So we define S of W as this plus S bulk of V. Okay. Now I should tell you that so far, I mean, at this stage, you're not talking about any error correction code, right? This is a purely a bulk analysis in the geometry. Okay, and this is some result. Okay, that so far it's all definitions, right? I'm now going to give the result that that comes out of this eventually. So V is the region bounded by W and R. So this is the bulk entanglement. Now this one is, so this is what I said. I mean, when I said precise formula, okay, this is not so precise. Okay. This one is somewhat ill-defined. Due to UV divergence. In entanglement entropy. Okay, we had seen already UV divergence in entanglement entropy in the context of boundary. Okay, but there at least we had an idea of what the regulator is. Okay, this S bulk, okay, we really don't know how to compute it in a way that is ultraviolet finite. Okay. Now, the point is in string theory, you are supposed to not have any ultraviolet divergence. Okay. Problem is the string theory can only compute things which can be computed. Okay. And this object, okay, is not really something that we can expect to be a well-defined object in the full quantum gravity. Because this is, I mean, as we discussed, in quantum gravity, we don't expect any local observer, right? And this quantity is certainly something that is local in the bulk. Okay, it's not something that is computed from asymptotic region. Okay, so it's not, so we don't expect that this actually makes sense fully in the bulk. Okay, or in any theory of quantum gravity, but in some semi-classical notion of this should exist, that you think of this as a quantum fields fluctuating in the background geometry. Okay, and one should think of it that way. Okay. But the problem is that if you think of it that way, then it's not quite clear how to regulate the UV divergence. Okay. Now, normally you will see statements that the UV divergence of this is supposed to cancel against the renormalization of Gn. Okay. Now, the problem is that in string theory, Gn is finite. Okay, Gn, of course, in a theory of quantum gravity, Gn has renormalization. Okay. But in string theory, even if there is renormalization, it's a finite renormalization. Okay, and we understand how what that is, because Gn is related to S matrix. And S matrix is something that is well defined in quantum gravity and is computable. Okay. So in this sense, it's not completely clear how to make sense of this. Okay. But let's just proceed by in a somewhat semi-classical sense. Okay. And see what you are supposed to do. Okay. So then the idea is that we find W that minimizes S of W. Okay. So we minimize not just the area, okay, which was the original Ryu-Takayanagi formula, okay, but area of W together with this one, okay, the bulk entanglement entropy inside of this volume. Okay. And minimal,
Left-hand side.
pardon?
I said in the left-hand side, should it be S of R, means that is the entropy, entanglement entropy, or?
No, we choose a W, right? Any W
Yeah.
we choose. And for that W, we calculate this and we calculate this, right? V is defined only by after specified both W and R. So these are the
So this
definitions.
is like the most general thing one would expect for S of W of this form. It's
Yeah.
like kind of
So I'm
like
not saying that this is entanglement entropy yet. This is some definition.
Oh, okay.
Okay.
Oh, actually.
So the point of minimal of SW gives the entanglement entropy. So this is the general result of R in the boundary. Okay, so this result, as I said, this was not derived using any holographic code or anything. This is a quantum field theory result. And you can look, I'll give the reference, 1307.2892, I think. So this is by Faulkner. Which because they proved this general result. And the way they proved it is that they started with the definition of entanglement entropy in the boundary theory. Okay, using the, so there is a procedure by which you can calculate entanglement entropy in quantum field theory, which is using the replica trick. Okay. And then they tried to convert that path integral in the boundary, okay, which the replica trick gives, into a path integral in the bulk theory, okay, using the DSC FTD study. And that's the way they eventually arrived at this form. Other questions? So the tensor network model, as that is, yes.
Could we have made any sense of black hole entropy in this format?
Yes, we can indeed. Because you see, imagine that, okay, maybe I'll say it. Imagine that you have a black hole in the bulk, okay? Let me just describe the Ryu-Takayanagi formula. The entanglement, bulk entanglement comes as an extra input. Suppose you have a black hole here. Okay. Now consider this a small region in the bulk, in the boundary. Okay, R. Okay. So then the minimal surface is this one. Okay, it will be close to the boundary. and we'll see that the minimal surface is the area. Okay, so the minimal surface W is small. So S of R is area of W over 4GN, which will be almost 0, okay, because area of W is 0. Now let's look at the complement. Okay. So here the problem is that we cannot choose this one, right? Because this is not homologous to this region. So we can choose a surface. So let me go one surface. So it could be something like this. But the minimal surface, okay, if W is really small, then the minimal surface is not this one. The minimal surface is actually the union of this and this. Union of this and this is actually homologous to this region, because when you try to deform this, okay, you can use this to cancel it out. So for the complement, okay, so S of RC, if we call this RC, S of RC will be given by area of W over 4GN plus area of the horizon by 4GN. Okay. So this is almost 0. So you are left with area of horizon over 4GN.
So, but I mean, if the boundary was in pure state from the beginning, then the entropy contained in region R should be equal to that of region RC, right?
Yes. So that's precisely the point. So what this is saying is that the boundary is not in a pure state.
Okay.
Okay. So this is basically saying that the black holes. So basically the entropy of RC is the black hole entropy. And so this is basically saying that the boundary is in a mixed state. Okay, in fact, more precisely, it's in a thermal state, which P as a black hole temperature. Okay. So that entropy of RC is actually the black hole entropy. RC is basically the whole region now, right? If R is shrunk to 0, RC is basically the whole of boundary. And what this black hole entropy is now counting is basically the total entropy of the boundary. So that's the interpretation of black holes in this picture, that if you have a black hole geometry, then that means the boundary is not in a pure state, but it's in thermal state. Okay, so now let me come to the final point. So basically what we saw in this, so the result that we saw are similar to the ones we found in the holographic code. Except that for the holographic code, most of the results are upper bounds instead of equality. So this problem, in fact, was resolved. Okay, so this is, I'm not going to discuss this any further, but I'll give the reference. Using what they call random tensor network. Where it is like a tensor network, except that at each bulk site, you put a random network. You don't put the same tensor network, same perfect tensor at every boundary, every bulk site, okay? But you put some random tensors. Okay? So this basically shows that all the inequalities actually become equalities in this case. Okay, and it reproduces exactly what the analysis from ADS-CFT gave us. Okay. And in fact, it also shows that the information from the bulk region V is encoded in R for the minimal surface. Okay. So this is what is called the entanglement to edge hypothesis. The V, let me remind you what V was. So V was basically this region between R and the minimal surface now. Okay. If the minimal surface is this one, then V is this region. Okay. And the entanglement to edge hypothesis, right, which again was basically discussed independently in the context of ADS-CFT, okay, was that this the region of the bulk that is bounded between the RT surface, okay, which you get by extremization, and the boundary, okay, the boundary segment whose entanglement and entropy are trying to compute, okay, that region can actually be encoded in R, okay, which in this case means R1 union R2, okay, and this result also automatically comes out from this analysis. Okay, that once you have determined the minimal surface, okay, what they show first of all, that the entanglement entropy is indeed given by the minimal, by that general formula, okay, namely this formula, the minimum of this. Okay. And once you have determined the cut that minimizes this, okay, then the region that is bounded between that cut and the boundary segment R, okay, that information about that region is encoded in R, which basically means that the operators that act inside that volume can be pushed to R. Okay, they don't have to be. There are other ways of pushing it when they are pushed somewhere else, but that they can be pushed to R. Okay, and that's the entanglement hypothesis. analysis. Okay, so I think I'll stop here, and this is more or less the end point of this set of topics. Okay. So later on, I may give a few lectures on this island, but that will be independent of this. So I think as far as this course is concerned, this is the end of this course. Okay. But the end doesn't mean that you should stop here, because I think these papers you should certainly try to read. Okay, I think all of these are quite readable. Okay, this paper as well as the this Pastarsky the Harlow skill paper. Okay. And here you will certainly find many more details. Okay. And essentially, I think these papers can be read with knowledge of quantum mechanics, right? Because it's basically mainly quantum information theory that you use to do all this analysis. Okay. And so later on, as I said, if I give these lectures on islands, which basically starts with this formula and proceeds, then I'll send out a message, okay, to the same group. Okay. But it will probably not happen next week. It will happen maybe sometime later. Okay, so I think I'll stop here. Are there questions?
Sir, in this black hole example, we didn't compute this S bulk of V.
Yeah, so that's the correction to the black hole entropy.
But that also like adds on to the entropy of RC, the like overall region.
So that you can think of as a quantum correction to the black hole entropy. Okay, so this is a classical formula, but it is known that the classical formula to black hole entropy gets quantum corrected.
Okay.
So that just gets added. You're right.
I mean, that does not get added to the black hole entropy, right? Because it's the region between the green surfaces.
Yeah, but the point is that the entanglement entropy actually depend on the surface only. Because that's what the entanglement is across, right? In a local quantum field theory, right, the entanglement entropy of a region is essentially localized on the surface, because the degrees of freedom are entangled across the surface. So that is also proportional to the area of the black hole horizon. If that's what you are, it's not a bulk. It's not proportional to the bulk volume.
Yeah.
It's also proportional to the area of the horizon.
The region between the green and the blue, this dashes.
Yes.
That is what contributes to S bulk of V, right?
Yes, except that the entanglement entropy of that region, right? If that region is in the vacuum, then it's coming essentially from entanglement across this horizon.
By across, you mean between inside and outside?
Yes. But quantum effects.
Yeah. Okay. Yeah.
Okay, it's not a classical formula. There are quantum corrections to this.
Yeah.
And for example, the logarithmic correction. There are logarithmic corrections to this. There is a proportional log of area. Right? Those are quantum corrections to the black hole entropy.
Yeah. Okay.
Sir, you said that at the end you will give that example where in C0 intersection C0 prime is not equal to when they do not coincide. That example you will give. That is in the presence of black holes. That was
No, I mean, okay. When they're not equal, C0, it may be something like this. No, I mean, let me draw. That after when you are doing this algorithm, right? You start with R, and you may reach a C0, which is like this.
Right.
And you start with R prime. Okay, sorry, this is, we have called it P prime and Q prime, right? So let me use that. Start with P prime, and this is Q prime. So it could be that C0 is this form. This is C0. And C0 prime is like this. So C0 intersection C0 prime is just this part. This one, the links that are cut by this, and the links that are cut by this. Right? So this is C0 intersection C0 prime, but it's not a cut.
Right.
So you cannot apply the earlier formula on this, but the number of cuts in this provides a lower bound. And that's the result that this paper proves.
Okay.
So in all this error correction code, our claim nowhere is, our claim isn't directly that this tiling is actually how information is encoded, right? This is just a model.
Well, yeah, it's just a model, but if it produces all the correct features of ADS-CFT, right?
Yeah,
Then
we'll accept.
Yeah. Okay. See, the point is that it is still a model in the sense that you are not. There are each ADS-CFT correspondence uses a specific quantum field theory and a specific theory of quantum gravity, right?
Yeah.
Of course, if you want to establish that connection, right, you have to look at the degrees of freedom of the particular quantum field theory, and then see how those are related to the degrees of freedom in the bulk.
Yeah.
But this general class of models, the fact that this has all the features, means that it seems likely that whatever quantum field theory you use, it will use this class of constructions, right, for encoding the bulk information in the boundary.
Yeah.
Yeah. So by the very fact that you are not talking about a specific ADS-CFT correspondence, this will remain a model, certainly.
Yeah. Also, I wanted to ask whether is there any sense in which we can call two particles as entangled if they do not share a common causal past? In the sense that
entanglement doesn't require a causal past, right? You can define entanglement if a state like this, right? Imagine that you have two particles, one here, right? And the state is up, down plus down, up. Then they're entangled.
Yeah, and no one stops me from specifying this regardless of where these particles comes from. But like suppose in the Big Bang universe, where we have some suppose, and also assuming that we do not know what happens exactly at the singularity. So these horizons that we have of the past, where we really don't know what is beyond the horizon. Strictly speaking, in quantum mechanics, we can still write down a bell pair where one of the particles is on outside the horizon.
Yes, certainly.
But does that make? But they haven't. But these two particles have never interacted in their past.
Yeah. The point is we don't understand the quantum mechanics near the beginning of the universe sufficiently to know whether such a state is possible or not. Whether universe actually created such pairs across the horizon.
Yeah. So, would a complete description of the universe entail this also? We need to specifically comment about things outside our horizon.
Yeah, my feeling
is
that, yeah, I think my feeling is that once you accept inflation, right, then these will also all get washed out.
These correlations.
Yeah, because whatever we see, right, in the visible universe was definitely within each other's horizon, right? If you believe in inflation.
Yeah.
So this question becomes academic, right?
Okay.
At least naively, it becomes academic.
Also, the comment about this single, is there a possibility of a finite past, within string theory, let's say? In Big Bang theory, we have a finite past, right? Because we don't also want infinite inflation.
Yeah. So the point is, okay, see, it's not even clear the meaning of whether the notion of time makes sense in the past, right? When there is a singularity. So the question itself becomes ill-defined,
Okay.
right? You can say that there is a finite past, okay, till the time the curvature reaches the Planck scale. That is a sensible statement. But whether the beginning of the universe was at a finite t or not, right? It's not even clear that is that question itself we can address in because quantum effects become so important in the past.
So do we need to like wash away all notion of space-time at Planck scale?
Well, you don't know. I mean, if you knew how to deal with the Big Bang singularity, then you will have answer to all these questions, right? But it's just that we don't know what happened at the time of Big Bang, right?
Even within string theory.
Yeah, even within string theory. I mean, in principle, these questions should be answered, but it has not been answered.
Okay.
Okay. Any other question? Okay, so if not, I'll stop now. Okay. And as I said, the next week probably there will be no classes. I'll see. I mean, when I can give those extra, maybe 2 lectures or so on islands. But I'll send out a message. Okay, I'll stop now.